Hello, and thank you for joining the presentation. I'm Schuchardt. I'm with TU Munich's Data Analytics and Machine Learning Group, and in the following, I'd like to present our work on collective robustness certificates. Before diving into technical details, let's briefly talk about the problem we are trying to solve. There are various machine learning tasks which involve making multiple predictions based on a single input. For example, classifying all nodes in a graph or detecting multiple objects within a single image. Up until now, methods for robustness certification have only been concerned with single prediction tasks, such as classification, where we're mapping a single input to a single output. The novel question we are trying to answer is how we can certify collective adversarial robustness. That is, how can we determine how many predictions are going to remain consistent under attack? For this particular project, we've decided to focus on classification based on graph neural networks. But before looking at them, let's briefly talk about how you would certify collective robustness up until now. You would simply iterate over your many predictions, certify each one independently, and then count how many are going to remain robust. Where that yields a valid certificate, it's going to be overly pessimistic because it implicitly allows the adversary to perturb each of the predictions using a different input. For example, if you think about node classification, the adversary may construct a different set of edges to attack each of the nodes, which is of course not realistic because in practice we only have a single shared input instead of many. We are trying to remedy this by combining the single prediction certificates in a more intelligent manner that models this single input. For this, we need two ingredients, the first of which is locality. Graph neural networks are typically local, meaning they make their predictions based on small receptive fields. Thus, not all perturbations necessarily affect all predictions, and therefore the adversary is faced with the problem of budget allocation. Where do they perturb the graph in order to cause the most damage to as many predictions as possible? The second ingredient we need is linear certificate encoding. We want to be able to evaluate these single prediction certificates efficiently based on evaluating linear constraints. You'll see in a moment why this is important. We do so by encoding the Pareto font in adversarial budget space. Let me visualize this for you. Let's say we're concerned with deletions of edges and of attributes. We can then think of any single prediction certificate as partitioning the space into certifiable budgets K and its complement. Alternatively, we may think of the Pareto font, the blue squares here, separating the two. If we're to the upper left, we're guaranteed to be robust. If we're to the lower right, the robustness is unknown. And that's basically all we need. Let's bring these two ingredients together. Thanks to locality, we can certify robustness for a single particular attacked graph by aggregating the amount of local perturbation within each receptive field and then evaluating the base certificates, the single prediction certificates, based only on this local amount of perturbation. Now, of course, typically you're not interested in a single attack graph, but in a whole set, a whole threat model. For this, we can formulate an optimization problem in which we're looking for the worst case graph from some large threat model B. Thanks to our linear encoding, this can be formulated as a linear program which can be efficiently solved. Now, let's look at some results. The method is quite simple, but it leads to drastic improvements. For example, we can certify robustness for orders of magnitude larger amounts of perturbations. In this particular example here, we're considering different citation graphs, while the naive method can only certify about a dozen perturbations, we can certify robustness even for thousands. Secondly, our method is model agnostic. It is compatible with any graph neural network as long as we know its locality and can certify single predictions. Finally, we're compatible with any single prediction certificate, such as interval bound propagation, convex relaxations, or randomized smoothing. That's about it. Let's summarize. We're combining single prediction certificates in a more intelligent manner by explicitly modeling locality and a shared input, and can thus obtain stronger guarantees. If you have any further questions, feel free to join us in poster session 10, 1 AM Pacific time on May 6th, or 8 AM Universal time. See you then.